that they concluded that fundamentally the United States couldn't afford to go back to the moon. I didn't believe that, and we wrote this paper in an effort to show that it wasn't true, and I think we succeeded. So before we start off, I want to address the issue of why we want to go to the moon. What's the purpose of return? And fundamentally, I think our goal is to extend human reach beyond low Earth orbit into cislunar and then finally into interplanetary space. By human reach, I mean not only the ability for people to routinely go there to do whatever job they may have to, but robotic machines as well, and people and machines working together. I think one of the lessons of the shuttle station program has shown us is that people and robots working together in space can build large, big, distributed systems of much greater power, flexibility, and usefulness than individual one-off satellites launched by themselves. So if that's our goal, that's sort of what we're after, how do we achieve that? Well, what we've chosen to pursue is the idea that a permanent base on the moon manufacturing propellant from lunar water is the key to opening up cislunar space. So our goal is to establish a robotic and human presence on the moon to use the local resources, specifically lunar water that we now know exists in quantity at the poles, to create a new spacefaring system. So how do we do this? Well, you've heard some of these good thoughts today in some of the earlier talks, the first one in particular. I think the key to doing this is to adopt a flexible, incremental approach. But incremental is not good enough. It has to be incremental and cumulative. Each increment adds a certain level of capability, and the previously in place parts work together with the newly arrived parts to create a much greater capability with time. So over time, as you build up assets on the moon, you basically have a much greater capability than you did before. And so your machines have to be designed to go to the moon and operate for very long periods of time, because we want them to operate for years, not months. The idea is to go to the moon using these small incremental cumulative steps. You can do that with machines first, with robots before people, because the moon is close. It's accessible and close. And by close I mean it's only a 3 light second round trip, which means you can teleoperate robots on the moon from the Earth. So our initial phases of lunar presence can be actually operated completely by remote control from the Earth. The accessibility part is even more important, because effectively a launch window to the moon is open constantly. You don't have to wait for planetary alignment. And when you do you don't have to wait for alignments that actually have very short duration, so you have a very narrow launch window. Our other goal in creating this architecture was to fit under the run-out budget given to the Augustine Commission. Now, I know that this is now moot because that budget has gone away, but at the same time, I think it's a good starting point. It shows you what you can do with a budget that's realistic in comparison to the actual NASA budget. A key thing here is to make schedule the free variable. So we're not so much concerned as to when we get back to the moon and what deadline we have. Money is the constraint here, not schedule. It's the inverse of Apollo. So I've got a detailed outline or a detailed description of how all these parts fit together. The paper is on my website. I'll give you the link at the very end. You can go down, download it, and read it. But in effect, what I've done is I'm going to summarize the approach in 3 slides. Basically, we use robotic assets first for the first several years, each building up, creating an interlocking capability, and then people come. But our initial steps on the moon are robotic. First step is to put a communication navigation system in orbit around the moon. This is important because in the polar areas, many parts are out of contact with the Earth, out of line of sight, and you need a communications relay to have constant communication. Since we're doing everything by remote control, we need that. In addition, you need a high precision GPS so you'll know exactly where you are, because the polar area is a very confusing environment. It's mixtures of light and dark. There are great changes in topography. You need to know exactly where you are at any given time. The first missions are polar prospecting rovers. These are basically rovers that have instruments that can prospect and map the extent and concentration of water at the poles. We use 2 of them. We put one at the north and one at the south, and then pick which pole has the most promising thing to offer. So in effect, we have the Lunar Polar Volatiles Explorer class rover mapping out the polar deposits at both poles, from which we pick out the actual location of the lunar outpost. On the same mission, or shortly thereafter, we can also fly what I'm calling an ISRU demo. It's a very simple demo to dig up some of the feedstock, the ice-bearing regolith, heat the regolith, drive off the water, collect it, and see if you can actually concentrate water. So it's merely a matter of collecting what's there and putting it into a more concentrated form. That's the demonstration. Once we've done that, we start delivering the robotic equipment to do the actual processing. And these are actually not big devices. They're on the order of MSR kind of rover-sized vehicles that basically dig up the feedstock, transport it, extract the water, and then store the water. Everything that we process on the moon in these early stages is stored, and we can do that at the poles because we have these cold traps that are very cold. Ice put in those areas will be effectively stable there forever. So you can actually start to build up a stock of water before people ever get there. The next thing we want to do is to actually demonstrate that you can crack the water into its component gases, and then you can freeze those gases into their cryogenic forms. So effectively, this is the demonstration of the fact that we can make propellant on the moon. In addition, there's some supporting equipment, including robotic landers. Power plants are basically erectable solar arrays that track 360 degrees around the vertical axis so they can track the sun. We're going to the poles because the sun is always at the horizon there. So we'll pick an area that's in quasi-permanent sunlight and install a variety of these power plants. Each one with the erectable solar array generates 25 kilowatts, and we've budgeted 8. So we'll have effectively twice the power level that ISS has now to operate this facility on the moon. And finally, cryogenic storage, which we're really helped on this by the lunar environment because the permanent dark areas near the poles, some of them are as cold as 25 Kelvin. So effectively, that helps us a lot with keeping the cryogens stored. But again, we're not necessarily going to make them all into liquid oxygen, liquid hydrogen until we actually need them as propellant. Finally, I should mention that we have 2 space-based assets. We have fuel depots in LEO. We ultimately have 2 of them, and that's basically to fuel the transfer vehicle that goes back and forth between Earth and Moon. And we have 1 in low lunar orbit to fuel the lander, which goes back and forth between low lunar orbit and the lunar surface. That's a trade, by the way. We're baselining low lunar orbit first because we think it's the optimum delta V solution. But ultimately, I think L1, Earth Moon L1, might be the best place to put that depot. So how do we complete this? Effectively, we now develop big landers that can transfer people and cargo. It's the same lander, there's just a cargo version and a people version. The lander can be operated remotely. And I'm talking about here a 30 metric ton class vehicle. I'm not talking about Altair with a 50 metric ton behemoth. I'm talking about something that's more limb-sized that can be fueled and reused, refueled on the moon and refueled at the depot in low lunar orbit. In the cargo version, it will actually transport the fuel that you're manufacturing on the moon back up to the low lunar orbit vehicle to create a fuel depot for both vehicles returning back to the Earth and ultimately for propellant that we want to export to cislunar, because our ultimate goal here is to create a cislunar transportation system based on the use of lunar propellant. The last steps include the surface habitat and surface infrastructure for the actual outpost. Basically, we're talking about habitats, we're talking about radiators and thermal control systems, we're talking about electrical power, cables. A lot of what we need in terms of the local infrastructure, we plan to make from local materials. So in effect, this is an experiment in the beginning to use local resources to actually generate new capability. One of the things we want to do is to take rapid prototyping equipment where we can take feedstock and actually make parts using rapid prototyping 3D printer technology. Another thing we want to do is very simple. Basically, Larry Taylor has shown that you can microwave lunar soil and cinder it into a glass. We'll use that to make landing pads, roads for the rovers, basically all the supporting infrastructure of the lunar outpost. All right, I know there's a lot here. You can read this in detail in the paper. The key thing to take away from this manifest and schedule is the vertical column shows the number of different missions. The arrows on the right show that once you land an asset or place an asset in space or land an asset on the moon, it becomes available for effectively indefinite use. We recognize some of these things aren't going to last as long as we hope, but in fact we've actually budgeted enough money to include replacements for those things that stop working. At the bottom shows where our production milestones are. Basically by year 5 and about the 6th or 7th mission, we're actually starting to produce 10 metric tons of water per year. And our endpoint after 16 years is 150 metric tons of water per year. The cost sheet shows where all the money goes. And again, I know this is an eye chart. I don't expect anybody to absorb it. But I want to point out 2 key things on this chart. First, we have a pointer here. That wasn't the one. Well, I got the pointer working. Sorry about that. All right. Are we having fun yet? Okay. This pink column here is for a heavy lift vehicle. So we've actually budgeted in the production of a heavy lift launch vehicle. We don't need this to do this architecture. We do it to make things simpler at the human arrival phase. This is not an Ares 5 class vehicle. This is a 70 metric ton heavy launcher. In fact, what I wanted to use was shuttle side mount because that was the cheapest, easiest way to get a good heavy lift capability with the minimal amount of ground investment infrastructure. The other thing it includes is 2 versions of the CEV, a Block 1 for use in near-term space station transit, and a Block 2 that basically is the one that goes back and forth between lunar orbit and the Earth. And of course, I couldn't resist putting this in a sand chart version. I call your attention to this black line. This is the Augustine runout budget. This was the constraint they were given and what they did to. This is the number they said they couldn't meet. We get all of this underneath that budget. And in case you're wondering how this was costed, we basically took existing cost models for robotic missions, added 50%, and summed them up. Now, what can you do from a growth option with this? Effectively, there's a lot of things you can do, make minor tweaks in the program depending on your resources and which direction you want to go. But fundamentally, since our goal is to create this constant transportation system between Earth and Moon, increasing the level of fuel production is one of the first things we want to do. We can also reuse the cislunar transfer stage. At the moment, we're discarding it, but effectively, we can actually develop this, modify this to where we capture the cislunar transfer stage, refuel it for its return journey to the Earth, allowing us to transport back to Earth orbit substantial amounts of lunar material. Now you may say, why would anyone want to do that? I can think of a lot of reasons. If I want to build some kind of a space facility that's in high lunar orbit or in the Van Allen belts, I might need lunar regolith for shielding. We can do that kind of thing with this kind of capability. Okay, so in summary, we create a permanent cislunar space transportation system based on the use of lunar water. And the infrastructure and systems are in place robotically first. People come later when they're ready, when we're ready to accept them and when there's a place for them to stay. All that's in place by the robots first. Small incremental steps build together and work together. They can't be independent of each other. It's all got to be part of an integrated system. The neat thing about this program is you can make progress no matter what your budget is. So if you tell me I can't have this much money in the next year, all it means is I slow down my schedule. So effectively, it allows you to return to the moon. You always keep your goal in sight. You don't have to worry about meeting a deadline. This incremental approach greatly encourages both international and commercial participation. Because you're using all these small pieces, anybody can get involved in this at any given level. Commercial entities can get involved in a small way by building subsystems of individual pieces. The international partners can provide individual systems themselves. And finally, they can all work together. I look upon this as a system that creates what I call a transcontinental railroad in space. And in the same way the transcontinental railroad opened up the North American continent to economic development, this system will open up cislunar space to economic development. And I summarized everything I've just said on this one slide, and I'll be glad to take any questions. Thank you.
Thank you, Paul. Any questions for Paul? No comments? No questions? Okay. Paul, what's your website?
Oh, I'm sorry. It's SpudisLunarResources.com. And this paper is on the front page, so you'll find it. There's one in front here.
Hello, I'm Kimberly Land, and I work with the Exploration Technology Development and Demonstration Program at NASA. And it's a program that has a lot of these projects already in existence. Have you been in touch with people like NASA's Exploration Advanced Technologies to see where we could go from where they currently are to where you want to go? Because it might help so you don't have to recreate. There's like 23 projects.
Yeah, well,
that
actually,
totally would love to have your input and probably leveraging.
I actually haven't really created anything here. Mm-hmm. I've just put together existing pieces into a system that makes sense from. I think the key thing that's been missing up till now in NASA's return to the moon, it's not money. It's understanding what your mission is.
Right.
NASA never understood why they were going to the moon, so they wasted a lot of time and money trying to figure out how to recreate Apollo, and that wasn't ever the mission.
Well, and I think a lot of it, too, is understanding how many people are still very passionate about it. So that's why I brought it up, because there's so many things that I already see. I'm like, yeah, we're doing that. But we can't go so far because of the money. So in a lot of ways, we're stunted, and we lose a lot of people because they can't fund their labor. So that would be a good thing to just try to see if you can bring it together. But very interesting. Thank you.
One last real quick question back.
Luis Riofrio, University of Houston. I've been working in Building 31 on regolith and ISRU studies, and your papers, which I've read, they show infinitely more planning, preparation, and knowledge than I've seen coming out of HQ. My question is, would you like to be administrator?
No.
Thank you, Paul.